Hi, good morning everybody. So now it's time to start the second lecture in Irit Dinur's course on PCP.
Okay, hi. So I wrote on the board the things that we talked about yesterday. Let me just go over them and then continue. So I just wrote two formulations of the PCP theorem. The classic formulation, thinking of it as a proof system, says that for every language at NP, we have a verifier, V, that reads the input, and its goal is to decide if the input is in the language or not. In addition to the input, it reads a logarithmic number of random bits, and which we denote by R, and some constant number of bits from the proof. So after it reads the random bits and the input, it decides where to read from the proof, reads a constant number of bits, the proof is denoted by, and then it says yes or no. And it has the following two properties called completeness and soundness. If the input is in the language, it says yes. So since it's working on random bits, we have a probability over the random bits, and the probability that it says yes is 1. If the input is in the language, there is a proof so that it always says 1 on this proof. And if the input is not in the language, so it's supposed to say no always, no matter what proof it's given. But so for every proof, it doesn't always say no, but the probability that it says yes is bounded by 1/2. So on half of the random coins, it's guaranteed to say no. On half of them, it might say yes. So it's not it's a probabilistic statement over its random coins. And the equivalent form is just as an inapproximability result. It says there is a reduction from every language in NP to a constraint satisfaction problem. So before I continue this formulation, let's just formally write what a constraint satisfaction problem. QCSP. CSP stands for constraint satisfaction problem. And Q stands for how many variables each constraint is looking at. So basically you have a set of variables, x1, x2, x3, up to xn. And these variables can have Boolean values 0, 1, or maybe some larger set of values called the alphabet. Okay, so they have some alphabet. Think of the alphabet as being 0, 1. Sometimes it's 1, 2, 3 for coloring, various things. And then we have a bunch of constraints. Let's call it C1, C2, C3. Usually more constraints than variables, Cm. Okay, and each constraint looks at some Q variables. So each constraint specifies which Q variables it's looking at, and it also specifies which values it is allowing, it will accept. Which values that he will see here will cause the constraint to say, okay, I'm satisfied. Okay, so that's a constraint satisfaction problem. And we say that, so the instance of the constraint satisfaction problem is all of this. So you specify each constraint, which variables it's looking at, and what are the conditions that will cause it to accept. And then we say that we have this notation of, say, call it sat of C, is the maximal fraction of satisfiable constraints, meaning you go over all possible assignments to the variables. It's just a definition. It's not an algorithmic thing. You go over all possible assignments, and for each assignment you count how many constraints it satisfies, and the maximal fraction is this value, right? So if a constraint system is perfectly satisfiable, we can write it as sat of C equals 1. And if you know that for every assignment no more than half the constraints are satisfied, this means that SAT of C is at most 1/2. Yeah, you can also, sometimes it's convenient to look at the unsat value, or how many constraints are guaranteed to be falsified, and that's 1 minus this value. I write it here. Unsat of C is just, by definition, 1 minus SAT of C. Okay, so now I can finish just the second form, and from now on we'll forget about the classical form and just look at this, okay? So just, there is a polynomial time reduction from every language in NP to such a problem, a CSP problem, such that you start out, the reduction starts out with an instance of the NP language, no matter what it was, and maps it into an instance C of the CSP, of max CSP. And then it has the following properties, that if the instance was in L, then the instance that is mapped to it is perfectly satisfiable. SAT of C equals 1. And if I was not in L, then the instance that we got is far from being satisfiable. No matter how you assign the variables, at most 1/2 of the constraints can be satisfied. So most of the constraints are going to be, half of the constraints at least are going to be falsified. Okay, and this is the basic PCP theorem, and this is the form that will be convenient for us in a hardness of approximation workshop to work with. Okay, so, right, so in fact, if there are questions, I'm happy to take them during the talk rather than at the end, so just try to feel free to ask if something is not clear. Right, so one thing that I want to mention, these are like an easy observation, is that it doesn't matter which CSP you're looking at. So CSPs, what are some examples of CSPs? So for example, 3SAT is a CSP, right? So we have a bunch of Boolean variables, and each constraint is an OR of 3 variables or their negation. So each constraint allows 7 out of the 8 possible values here. It says, you know, I'm not allowing 1, 1, 0. Everything else is fine. So that's max 3SAT. 3 coloring is also a CSP. Here, now the variables are the vertices of the graph, and they take values in 1, 2, 3. These are the colors. And each constraint looks at only 2 variables. It's just a constraint for every edge. And it says, I'm not allowing this color to equal this color. So that's how 3 coloring is also a CSP. Even max cut, right, is also a CSP. So these are just, again, the vertices of the graph. Each constraint says, I have a constraint for every edge, and it says this value should be different from this value. And in max cut, the hard thing is not to decide whether the instance is perfectly satisfiable or not, because that's easy. It's just deciding if the graph is bipartite or not. In max cut, the hard thing is to decide whether the maximal value of this is above some constant number smaller than 1 or below some other constant number smaller than 1. So max cut, and you know, and the list is long, and actually, you know, we understand these things somewhat well, pretty well under the unique gains conjecture. But the basic PCP theorem just says that for all of these CSPs, it is hard to approximate them to within some constant. So it's not only that these problems, it's NP hard to decide if the graph is exactly 3-colorable or not, but there is actually some constant less than 1, say 0.9999, such that it's hard to decide if the instance is perfectly satisfiable or no more than 1 minus epsilon, where epsilon is a constant, satisfiable. So the first kind of somewhat trivial observation I want to make is that once you obtain such a result for 3 coloring, or for 3SAT, for one CSP, the result follows immediately for all CSPs. And the reason is because you can do a local reduction as follows. So so let's do an example and it will be clear. Suppose you've proven this statement for the specific QCSP that is 3 coloring. So it's a 2 CSP over variables that take 3 values. So you know already that 3 coloring is, it's hard to tell whether it's perfectly satisfiable or no more than 99%. And then you can take this 3 coloring instance and convert it into a 3-sat. How will you do it? Each variable here takes 3 values, so you encode it by 2 bits, y1 and y2. Okay, x2 is, y11, y12. x2 is y21, y22, and so on. So you create a bunch of Boolean variables where each old variable was converted locally into a bunch of new variables. And then you put 3-sat clauses that say that you're not allowing all 4 possibilities here because you're only allowing 3 values, so you will put some clause that prevents this. And also you will put some, if you have a constraint between x1 and x7, you will put some 3-sat clauses on the variables that encode x1 and x7 that will ensure that when this color is different from this color, all the clauses accept. And when this color is equal to this color, at least one of the clauses will reject. And this whole bunch of clauses that you will put depend only on how many variables encode x1 and how many variables encode x7. So it's like a little gadget. You converted one constraint into, say, 10 constraints, so it's just a constant number. And you created this new instance, and it's by a local transformation. Each constraint was converted into a bunch of local constraints. And what do you know about this new instance? If all the constraints were satisfied before, then you can encode them correctly and all the new 3-sat constraints are satisfied. But if at least epsilon of the old constraints must have been falsified, then for every constraint that's falsified, it was encoded by some 10 3-sat clauses, so at least one of them must be falsified. So again, you have some other epsilon prime, but also a constant fraction of the 3-sat clauses that are falsified. So what this is, this whole story adds up to is that if you have a hardness of approximation for one CSP, it implies the hardness of approximation for all other CSPs just by this local gadget reduction. Okay, and the gadget that I used, I mean, if you would have to do it as an exercise, it's an exercise. You would come up with some gadget, you don't know whether it's optimal or so on, it gives you some hardness of approximation factor. Historically, this was like the first achievement, and then people started to ask, but what's the best hardness of approximation factor we can reach? I mean, our algorithm only goes up to here. Can we actually prove hardness that meets our algorithm? And that's a lot of the talks in this workshop are concerned about it. For some results, we know to prove NP hardness for the exact factor using 2 things. Using, first of all, a strengthening of the basic PCP theorem that I will discuss today, and using much more sophisticated gadgets, ultimate gadgets, the long code gadgets. But even if you don't care about it and just use, this most stupid gadget, you still get this equivalence of hardness of approximation for all these CSPs together. One more equivalence that I want to highlight because it's a bit more important for us is reduction. So yeah, let's keep it this way. Let's show that hardness of okay, so I'm assuming, by the end of tomorrow we will have proven that it's hard to decide if a graph is perfectly 3-colorable or less than 99%. So assume this. This implies a hardness of a label cover. Right, so let me try to convince you of that. I won't be able to do it fully, but let's do the first part, which is really easy. So what is label cover? Remember, it's you have this bipartite graph, and you have a bunch of labels, so every vertex can get a label. This is just like assigning variables with values. And each edge says, I'm only allowing these pairs of labels, not all of them. Find me a labeling that satisfies the maximum number of edges. So look at the graph that I drew. Do I have a stick here? Yeah. Okay, so this is my bipartite graph. Okay, so I have a hardness of max coloring. So I have all the vertices of my graph here, and for every edge, I have a constraint here that just looks at two. It's a two-area constraint, looks at two vertices and says, I want these colors to be different. And see how I created for my graph a bipartite graph. Okay, this is one side, this is the other side. And what are the allowable labels? So all the labels these guys can get are just 1, 2, or 3, specifying the colors. And the labels that these guys, that such a constraint can get is out of all possible 9 values that it sees, it's only going to allow 6 of them, because 1, 1 is not allowed, 2, 2 is not allowed, 3, 3 is not allowed. Okay, so it gets 6 labels, and then the labeling is just assign 1 to 6 to all of these, assign 1 to 3 to all of these, such that you maximize the number of constraints that are satisfied. Okay, so the reduction, I hope, is clear. It remains to see that it has the right properties. So just see that if the 3 coloring, if G is 3 colorable, then of course all of the constraints are satisfiable. Then the SAT value of the label cover instance is 1. And what happens if G is at most, say, 1 minus epsilon 3 colorable, meaning every coloring falsifies at least epsilon of the edges. Okay, let me write it. Every coloring falsifies at least epsilon of edges. Then I'm claiming that the SAT value of this label cover instance is no more than 1 minus epsilon over 2. In other words, let's look at it differently. If here epsilon of the edges are falsified, I claim here that at least epsilon over 2 of the edges of the label cover must be falsified. And why is that? So think of this label cover instance. Think of the picture up there. No matter how you assign it, look at the bottom part. You're assigning a coloring basically to all the vertices. And we know that this coloring must falsify at least epsilon edges. So now look at the corresponding constraints, the ones that correspond to these falsified edges. For example, suppose this is one of them. Then it's a falsified constraint. These 2 values are the same values. Now this, how are you going to label this vertex? It's only allowed one of 6 labels that say, these labels correspond to only 2 different values here. So it must be inconsistent either with this value or with this value. So one of these 2 edges must be falsified. So for epsilon fraction of bad edges here, you get epsilon over 2 fraction of bad edges here, and you've proven a reduction from max 3 coloring to a hardness of label cover, and that's it. Now what's the main issue here? How will I say it? Main issue for us is that we want a bigger gap. So it turns out that to prove a hardness of approximation with optimal inapproximability factors, you want hardness of label cover not with the gap of 1 versus 1 minus epsilon. Okay, this is quite a small gap. It's just a gap of epsilon. What you really want is a gap of 1 versus, instead of this, you want this to be some epsilon, going to 0. Okay, this is the label. If we had hardness of label cover with a gap of 1 versus epsilon, we'd be in business. We can now proceed to do what probably Ryan has done yesterday and today and so on. So you want to amplify the gap. Okay, and this kind of brings me also to what I was asked yesterday at the end of my talk about the values of 1 and 1/2 here in the theorem, in the PCP theorem. And so someone said, this looks kind of arbitrary. Why did you choose 1 and 1/2? Couldn't you have chosen some other values? So I forgot to say that these values have names. This is called the completeness value, and this is called the soundness value. And this stems from this view of a proof system. A proof system has completeness and soundness. Completeness says everything that's everything that's true should be provable, right? So for every true statement there is a proof, and everything that has a proof should be true, and that's soundness. So here it says, if something is false, it shouldn't have a proof because it has proof. It's a contrapositive thing. So the completeness one, let's just keep it for now. 1 or 1 minus epsilon is fine. The soundness is what we want to make go down, right? Think of using the PCP theorem somehow. You want to really use it to check a proof. It's not enough that after you did all this work, you know that you were correct with probability 1/2. It's not very satisfying. If the probability of being correct was 2 to the minus 100, that would be more appealing. And it's a very easy thing to do, right? You have this verification procedure, you get a proof, and you run the verifier, you know that if there is a problem with probability 1/2, the verifier will find it. So just run the verifier again, a new random codes. And then again it will have probability 1/2, so together the probability of not finding a problem is already 1/4. So if you repeat it 100 times, you already got this 2 to the minus 100 very easily. And really that's it, I'm not cheating in any way. And if you want to see it in this formulation, then how will you, okay, and just before I say that, what I just said of rerunning the verifier again and again is called sequential repetition. You run it once, you run it again, you run it again. Sequential repetition, that's the buzzword that we call it. And how would it look if we forget about this verifier notion and just look at inapproximability result? Suppose we have such a reduction, okay? Then I claim we can just take this instance C and convert it into a new instance, which we will call C to the L. So we just convert, let's call it sequential repetition. You take the instance C, instance of QCSP, okay, and you convert it into C to the L. What's C to the L? So suppose C is some instance C1, C2, constraints Cn over variables x1 up to xn. Okay, so these are the constraints over the variables, just like in the picture up there. So now you create this C to the L. It's nothing but just taking the ands of L tuples. Okay, so for every choice of I1 in 1 to n, and then independently at random I choose I2 and so on. So I have this CI1, and then I choose CI2, CIL. And this is for every choice of I1, I2, IL in n. So this whole thing is in n to the L. I will have a new constraint. What does this constraint do? It just checks that this constraint is satisfied and that this constraint is satisfied and so on. Okay, so it's like taking an L tuple of vertices up there, looking at all of their neighbors and checking that all of the constraints are satisfied. So this is an instance of L times Q CSP, because it's looking at possibly L times Q variables. Q variables for the first one, Q variables for the second one, and so on. And notice that its size also, if the original thing was size n, this size is n to the L. So it's a bit of a blow up. But the nice thing is it's obvious, right? If you have an assignment that satisfies all of these, you have an assignment that satisfies all of these. But if you have an assignment, if you know that so let's write it, right? So sat of C is 1 implies sat of C to the L is 1. But if you know here that no matter what you do, the satisfying sat of C is no more than 1 minus epsilon, think of this as being 1/2, for example, then I claim that this is true. Thanks, yeah, L. Then the C to the L thing has, you can never satisfy more than 1 minus epsilon to the L, and the reason is whatever assignment you gave, you know that it falsifies at least epsilon of the clauses here. And so what fraction of the clauses can be perfectly satisfied? No more than this. So that's it. So this is very easy. So now we manage to, so if you choose L to be, if you choose L to be 1 over epsilon times, say, log 1 over epsilon, from a gap between 1 and 1 minus epsilon, you get a gap of 1 versus epsilon, right? Which is what I said I want, right? I want a gap between 1 and epsilon that is as close to 0 as I want. So I have this, what is called the low soundness error, right? A very, very big gap. So now all that remains, the only problem that I have is that this CSP, this new CSP, has this many variables per CSP. Each constraint looks at L times Q variables, and I want to convert it into a 2 CSP. And really, the same conversion from max recoloring to hardness of level cover can do this. You can always convert it back to a 2 CSP using this trick. But unfortunately, when you do that, your soundness goes back all the way up to being close to 1. So these two trivial or semi-trivial transformations kill each other. So you can never benefit by doing both of them together. Okay, so the issue is that we know how to get small soundness error. We just don't know how to do it with a label cover instance. I mean, we today in class, it is known how to do this. The way to do it is by parallel repetition. There are a couple of ways to do it. One of them is by parallel repetition. But first, let me make another comment. The second comment I want to make relates to the size of the instance. It's also called right, so the size of the instance. So if I start out with an instance with n constraints, after I did this trick of sequential repetition, I got an instance whose size is much bigger. It grew to the power of L. Okay, it's a big blow up. Actually, it's very easy to do the same thing, but get the instance to remain roughly of the same size. Okay, to stay polynomial, it has to be independent of L. And the way to do it is by, instead of taking all possible L tuples, just take a collection of L tuples that is what's called a good sampler. Okay, because all you need to do is have these L tuples be a good sampler of a set of size epsilon. And so there are such things known as samplers, and you know that every assignment causes at least epsilon fraction of the clauses to be falsified. So all you need is that your collection of L tuples will hit a set of size epsilon with very high probability. Okay, and it's easy to do, and you can really. So we know. Okay, so let's just write it by using samplers or hitters. We can, and this is called the de-randomizing. The reason it's called de-randomizing is if you think of the verifier and how many random bits it's using to get the probability of error very small, then it can do independent sampling. It uses a lot of random bits, or it can recycle the randomness. So this is like de-randomizing. We can de-randomize sequential repetition. Okay, so we can really get the same behavior using expanders, for example, where the size of the instance is, maybe depends on epsilon, but in a linear way. Okay, now what is, okay, I only have this much. Okay, I only have this much for parallel repetition, so what can I be expected to do? Repetition. So parallel repetition is a transformation that kind of gives you the best of both worlds, right? It decreases the gap to this 1 versus epsilon, and at the same time, it leaves you in the label cover world because you remain with this 2 query thing. Now, maybe at this point, it's not clear why having a label cover instance with 2 queries is so much better than a constraint with each constraint depending on many variables. But I mean, when you start seeing these hardness of approximation reductions, you see that you take each variable and you use a long code to encode it, and once you have each constraint looking at too many long codes, you're in deep trouble. So the fact that the constraint needs to look at as few variables as possible is very important. In fact, right, in the unique games, it's really the constraint is looking at one variable, and then we really know how to solve it. Right, so parallel repetition says the following: if I have a constraint system C, no, forget about C. Let's just do a label cover. Okay, if I have an instance of label cover with gap 1 versus 1 minus epsilon, I can convert it to label cover with gap 1 versus epsilon by doing this, by doing this parallel repetition to the L times. And the thing is, I have this bipartite graph. Maybe I'll draw it in parallel like I did up there. So I had this bipartite graph with these clauses here, C1, C2 up to Cn, and the variables here, x1 up to xn. And now the conversion, it takes L tuples of variables and L tuples of clauses, right? And it compares an L tuple of clauses to an L tuple of variables that are contained within this clause. So if you forget about the fact that these are clauses and these are variables, just think of a bipartite graph where you need to assign labels to both sides. Okay, so now the parallel repetition will say, and call this, say, A, and this B. Okay, so now the construction will have A to the L here. So for every vertex will be A1 up to AL. Every vertex here will correspond to L things here. And every vertex in the bottom part will also correspond to some B1 to BL from the bottom part. And you will have an edge if there were edges coordinate-wise. Okay, now, and the constraint on the edge will check that all the L constraints have been satisfied before. So this is the parallel repetition transformation. And the theorem, the celebrated theorem of Ran, says that indeed the error goes down. And Ran will talk about it, I think today or tomorrow? Tomorrow, okay. So I guess he won't prove it, but at least he will state it in several forms and so on. So once you take, so we will prove that this is NP-hard. And this transformation, assuming that Ran's theorem is correct, shows that the label cover that Ryan wanted, we want for hardness of approximation is NP-hard. Yeah, sure.
So would you like to explain what parallel repetition means in detail, or do you expect Ran to do it?
Yeah, Ran will do it.
Okay.
But, I mean, I'm happy to answer. So this, you want me to explain this in a couple more minutes? I'm happy to do it.
Well,
yeah, let me do it again. Okay. So let's just rename these A and B. I have C and X, and I want it to be A and B. Okay, so suppose, let's start out with a label cover instance, which is a bipartite graph. And one part of the graph is called A, and the other is called B. And I have some set of labels allowed here and here. And each edge says, I'm allowing these labels, only this and this label will make me satisfied. And I already know that it's hard to decide whether this instance is perfectly satisfiable, satisfiability 1, or whether it's no more than 1 minus epsilon satisfiable. So this is my starting point. And now what does it mean to apply parallel repetition to this instance to get this? It means, just think of it as a combinatorial transformation. For every L tuple of vertices up here, I will have one vertex here. So if I had n vertices up here, now I will have n to the L vertices up here. Okay? And the same down here. For every L vertices down here, I will have one vertex down here. So again, I will have, if there was m vertices down here, I will have m to the L. And when will I put an edge? For every choice of L different edges, 1, 2, 3, up to m edges, what do these m edges correspond to? Well, look at the m tuple of top points. This is some vertex up here. And look at the m tuple of bottom points. This is also some vertex down here. And there will be an edge corresponding to this choice of m edges. Okay? So that is the construction. And what does the theorem say? Let's go say 1, comma.
Wait, I'm sorry. You put an edge between two L tuples if you have an edge above between all the individual elements?
Yeah, so if I write this edge, I really should have left more space, right? Let me erase this. I put an edge between A1 up to AL and B1 up to BL.
These are all the
Yeah, these are ordered. There's an edge in the label cover to the L if and only if the edge A1, B1 is an edge in the label cover, is an edge in the label cover, and A2, B2, AL, BL. Okay, so that's how I put edges. And what will be the constraint? Well, it will just check that. What are the allowed labels in this label cover? You need to say what are the labels. So the label is going to be just an L tuple of labels, and the label here is an L tuple of labels. And these two things are consistent if they're consistent coordinate-wise. So if I have an L tuple of labels for this vertex, I look at it coordinate-wise, and I check that this label is consistent with this part of the label is consistent with this part of the label, and so on. Okay, so when Ran describes it as a game with two provers, you will see it's more intuitive to think of it this way. And this is the combinatorial translation.
But what's the statement? Now it's just a construction.
Right, what's the statement? The statement says that, let's just do epsilon prime. That, if the original label cover was perfectly satisfiable, then so is this. This is actually obvious, right? Think of the labeling that satisfies all the edges here. Then it's obvious what you should assign here to the labels. Just the L tuples that correspond to that assignment, and everything will be satisfied. The main theorem to prove is that even if you assign somehow differently, so if this was epsilon far from satisfiable, you were in this case, no matter how you assign, epsilon of the edges will be bad, then there is no way that you can assign this instance with values without falsifying a huge amount of the edges, almost all of the edges, right? So you would expect to say that no more than 1 minus epsilon to the L fraction of the edges can be satisfied in this case, like in the sequential repetition, but that's not true. In fact, there is a way to kind of cheat or somehow, since the assignment sees the whole L tuple together, it can maybe use some correlation to get some better results. And all of this Ran will talk about. So you don't get this, but you get some similar, drawback. It's not even theta because it depends also on epsilon. So the real statement is that there is some other constant that goes down to the L, and this constant depends on this 1 minus epsilon. Okay, but this will be in another talk. Okay, so that's it. I don't want to get into it because we have other things to do. Okay, so now let's go to the next board, right? So we will do this. Avanti, okay. Okay, so now I want to go back to proving the PCP theorem itself, and I want to talk about a reduction from three coloring. So let's title Proof of the PCP theorem. Right? Okay. So I want to start with a three coloring problem, just a graph G. Okay. And reduce it to a gap 3 coloring or something like this. So I want to reduce it to a graph H. such that if G is 3-colorable, then also H is 3-colorable. Yeah. And if G is not 3-colorable, then H is far from being 3-colorable. Every 3-coloring of H falsifies epsilon of the edges, so let's write it this way. H is 3-colorable means that the satisfiability value of H is 1. Okay, or maybe I will call it, let's just leave it this way. You can satisfy all of the constraints in H. And if G is not 3-colorable, then H will have the property that you satisfy no more than 1 minus epsilon. Okay, so there is at least epsilon fraction of the constraints that are falsified. Okay, and this is our goal, and this is like the PCP transformation. Okay, and the way we will do it is, even here, think you have some kind of gap, right? When G is 3-colorable, the satisfiability value of G is 1, right? So, right, sat of G is 1. And when G is not 3-colorable, then what does it mean? It means that every 3-coloring of G falsifies at least one edge. So you can think of it as a fraction. 1 over E fraction of the edges are falsified. So set of G is at most 1 over E. Sorry, 1 minus 1 over E. Right, so you can satisfy almost all of the edges, but there is at least a 1 over E fraction. This is a ridiculous way to say it, but the reason I say it this way is because now you see that you have some kind of gap in between the two cases, between 1 and 1 minus 1 over E. And the only thing you need to do is amplify this gap and get this 1 over E to go to a constant epsilon. Okay, so the task is, I guess qualitatively, you can think it's similar to what we did in the board above, because we had some gap between, there it was between 1 and 1 minus epsilon, and we wanted to bring it to the gap between 1 and epsilon. So, so we already know of two ways to do it. We can do sequential repetition, which is, we proved that it works, it amplifies the gap. Or we can do parallel repetition, which someone else proved that also amplifies the gap. Right? But think, how many times will you need to do sequential repetition to get a gap of 1 over E to become a constant gap? At least roughly E times, right? So you need to repeat this random process of choosing a random edge and checking it E times. So by the time you did it E times, you read the entire graph. So your constraint, your check is no longer local. You're actually reading the entire proof. You haven't done anything. Same thing with parallel repetition. You still need the number of repetitions to be of the order of 1 over this value, so it won't work. What we will do is do it gradually, use a few steps. So we will map G to some graph G1 and then to G2 and so on. And each time we do this transformation, we will say double the gap. So if we start with a gap of the gap, let's think of it as the difference between this value and that value. Okay, so this is 1 over E. After one time, it will be 2 over E. After, again, it will be 4 over E. And we double it, so after you do it log n times, the gap becomes a constant. Okay, so this is this will be the approach. We want to double the gap each time, so we will show a mapping Gi to Gi plus 1 that doubles the gap. Or maybe a better way to think of it is that you look at the ansat value. I have this ansat value up on the highest board up there. Instead of looking at how many clauses are satisfied or how many edges are satisfied, look at how many edges are not satisfied. Okay, so you start out with an ansat value of 1 over E. So let me even write it this way. It's better. Ansat at least 1 over E, and here the ansat is 0. Okay, so at first we know that either the graph is perfectly, the ansatz is 0 or it's at least 1 over e, and you want to get a situation where the ansatz is like this. Okay, so either it's 0, you stay 0, or if it was something non-zero, it now becomes a constant. Okay, and the idea is that, so you double the ansatz value, and I don't write it, but of course if it was 0, you want it to remain 0. Right, so that's what the mapping will do. And the way we'll do it is by doing some kind of parallel repetition, some kind of twist on parallel repetition. So this transformation will have 3 steps. So 1, 2, 3. The main step is this amplification, or doubling the ansatz is like amplifying the ansatz, right? So we call it amplification. Amplification by a variant of, let me call it like this, just parallel repetition. Okay, so this is it's not exactly parallel repetition, but it's some kind of form of it. And then these 2 other steps are going to be correcting steps so that this actually is able to work a few times. So the first step is some making the graph into a normal form. So it's just, let's call it regularization. We really don't need to worry about it. Okay, so this whole thing is in parentheses. It's some step to make the graph easy to work with. Don't forget about it. It's not inherent. The main step is this amplification by some kind of parallel repetition. And then the other main step is, I guess, call it alphabet reduction. Okay, so let me now show you what these 2 steps are concretely. And then I will try to explain why we call them these things. And then tomorrow we will prove that, or at least sketch a proof of why these things work. Okay, so here is what is the amplification step. It's and you will see why you can think of it as a parallel repetition. So you have a graph. You have all kinds of vertices and edges and so on. And this is our Gi, and now we will create the Gi plus 1. And in this graph that if you view it as a 3-coloring instance, it's one of 2 cases. Either it's perfectly 3-colorable, or no 3-coloring colors more than 1 minus some fraction epsilon of the edges. And now what you do is do this. You take this graph and you have the same set of vertices exactly. Okay, so I won't be able to draw it, right? But anyway, you have the same set of vertices. But now the edges will correspond to some walks of some length, say walks of length 2. Okay, so if you had a walk of length 2 from this guy to this guy, you will also have an edge here. And so I didn't, okay, so edges. Okay, so if you think of the adjacency matrix of the graph, then the adjacency matrix of this graph is just this matrix raised to the power t. Okay? It's now a multigraph, and the weight is important. And also, I forgot to say, at this point you can, so this step of making the graph nice also make sure you have self-loops, for example, and stuff. So I don't even need that. But anyway, yeah, so just the adjacency matrix of this graph is the tth power of the adjacency matrix of this graph. And now, what are the labels and what are the constraints? So this is no longer a 3-coloring instance. This is going to be some kind of CSP instance, a general CSP. Right? So now, for every vertex in GI plus 1, we'll have a value that's supposed to tell you not only the color of this guy, but the color of all of its neighbors in this graph at length, at distance t. Okay, so one vertex doesn't only encode its own color, but it encodes the color of all of its neighbors in the neighborhood of radius t. Okay, so each v in GI plus 1 gets a label encoding all colors of neighborhood in radius t. Okay, so it's like each vertex polls its neighbors and asks them, I want to know your colors as well. Right? So, and the label that it gets doesn't only say what the color of this guy is, but what are all the colors of this whole neighborhood. Okay, and now what is the constraint? So for any two vertices that have an edge now, when are two vertices connected by an edge? According to this tth power of the adjacency matrix. So we know when we have an edge. So if you have an edge between this vertex and this vertex in GI plus 1, then these two vertices say, the constraint says, I want all of the labels to be consistent. So consistent means two things. First of all, the label of a vertex on its own labels an entire neighborhood. And it's not allowed for this label to give two colors to adjacent vertices that are the same color. So the labeling should be at least a partial view of something that looks like a legal 3 coloring. Right? So this vertex gets values for all of its neighborhoods. These values locally should look like they come from a legal 3 coloring. The same for this. And whenever these two labelings label endpoints of an edge, right? So these two vertices can actually be at distance, I don't know, some distance t or less than t from each other, maybe t over 2 from each other. Then both of these vertices label many of their common neighbors together. So all of the labels should be consistent, and they should all together look like they are a legal 3 coloring according to what they see. So in other words, these two vertices see some very small part of the entire graph. Okay, and their labeling tells them what is the 3 coloring of this part of the world, and this 3 coloring should be perfectly legal according to what they see. Maybe there's no way to extend it further away, that's too bad. But the constraint can only check what it sees locally, and so locally it checks that everything is fine. Okay, so it's a label. Constraint, just check local consistency and soundness. So locally everything is fine. This is what the constraint will check. Okay, that's the construction. Of course, now what do you claim about this construction? The claim is that if in G there was some epsilon, if GI there was some epsilon fraction of edges falsified, then in GI plus 1 the fraction will be something related to t times epsilon. Okay? So all we need is that it's 2 times epsilon in the end. So t will be some other constant because later we will lose something. So think of it as being 10 times epsilon. If here it was epsilon fraction was bad, here you will have 10 times epsilon fraction that are bad. So you manage to amplify the ansatz value. And of course, it should be evident from the way the constraints were specified that if this was perfectly 3 colorable, then just by taking the assignment that corresponds to the perfect 3 coloring, you get an assignment to this constraint satisfaction problem that's perfectly satisfying. Okay, so this part is easy.
GI plus 1, then it's not really a graph. It's a multi-graph with the labels.
That's right. Right. First of all, it's not really a graph, it's a multigraph, or you can think of it as a weighted graph with weights on the edges. And secondly, it's not a three-coloring instance. It's a multigraph, and each vertex gets a label, and each edge has some constraint. It's not a coloring constraint. You're not checking that this is different from this. You're checking something more complicated. But the point is it's a CSP. It's some local check that looks at only only two variables, and each variable is only over a constant alphabet. So how are we going to proceed from here? I mean, we can't apply this even once more because this procedure starts with a three coloring and moves somewhere else, so you can't even apply it again. So what you need to do now is take this instance and convert it back into a three coloring, and this is what I wrote here in alphabet reduction. So the way you convert back is similar to what I started out with in the beginning of the talk today, how we convert, say, a three coloring to a max sat, or how do we convert between two CSPs? We do some kind of local encoding. We take each variable. Now, this vertex, think of it as a variable that gets values from some very big alphabet, because the value should be able to encode coloring of an entire neighborhood. So you take this value, and you encode it by many, many little vertices. Each vertex will get one of three values, because you want to bring it back to a coloring instance. So we will take each variable and encode it by many little vertices. In fact, we will also have more new vertices for every edge. It would be a kind of a complicated gadget thing, and we'll put edges in some rather complicated way, and this will convert this G back to a coloring instance without harming the gap. So this second step of the alphabet reduction is actually much more I think conceptually it's more complicated than this step. This step you can kind of see what's going on. In this step you can either think of it, well, there is some gadget reduction that works, and that's fine, and then you know that it works. But if you want to understand how it works and why it works, what you really need to understand is how to compose. I mean, the way we construct this gadget is by another construction of PCP. So it's like there is some kind of composition or recursion going on inside here, and we'll talk about it a little bit tomorrow. Right, let me just, I know I'm 2 minutes over time, but let me just, one more minute. I want to just say, why did I say that this is... I have 4 more minutes, okay, thanks. Okay, so good. So the alphabet reduction is something that's related to composition, and I'll talk tomorrow. I think that this part is very important. I think this part is not utilized strongly enough. So I think it's worthwhile to go into it a little bit more, and I think people are a little bit, they don't like it so much, so I will try to spend some time on it. But this will be tomorrow. Today, let me just finish. Why did I say that this strange transformation is like a parallel repetition? It's because really we moved from some CSP to a CSP that looks at L tuples, where the L tuples were chosen according to the graph. The L tuples, what were they? For every vertex, you had an L tuple, which is just all of its neighbors, right? And you compared two L tuples according, again, to the rules of the graph, but again, you just checked that the constraints between two L tuples were consistent. So it's kind of similar to parallel repetition, except you don't take all possible L tuples, you only take part of them, and you check that's exactly what you do. Now, one more thing just to say before I finish. A very important aspect of this thing, and the reason we couldn't have just used parallel repetition without this strange de-randomization, without this strange taking part of the L tuples, is because parallel repetition blows up the size of the instance. If even you took GI squared in the parallel repetition from a set of n vertices, you would wind up with a set of n squared vertices. Okay, and you can't allow yourself to make, and you would double the gap, just like we do here. Okay, but you can't allow yourself to run, if you want to double the gap, you need to run logarithmically many times. And you can't afford to square the size of the instance logarithmically many times, right? Because then you would wind up with g to the n as your size. Okay, and you can't afford it. So the point of this transformation is some kind of a de-randomized parallel repetition in the sense that the number of different L tuples that you take is just n. If you started from n vertices, you wind up with n L tuples. Okay, so it's a very efficient parallel repetition. You don't take n to the L tuples, just n tuples. And this relates to, again, to the question of de-randomizing parallel repetition. I didn't mention it before, but it is known that you cannot get Ran's result with a de-randomized parallel repetition. It is known that if you want the error to go down exponentially, the size of the instance must also go up exponentially. This is a very nice result of Feige and Kilian. I'm interested in understanding whether this result can be, this impossibility result can also be extended. So a couple of years ago, in a beautiful result, Ran and Dana Moshkovitz proved another way to get small error, not through parallel repetition, through some other ways. And maybe, I think Prahlad will talk about it tomorrow or in one of these days. And but there, the instance doesn't go up exponentially with L, but the error probability also is not exponential in the L-related parameter. So it somehow gives you the feeling that the impossibility result can be strengthened further. Okay, but that's it for now.
Questions, comments? None. Thanks again.